We are continuing our treatment of the Debye model. So we almost done Debye model. Okay, so what we know, I remind you, it's the property of the solids, and we are interested in calculating the specific heat. Okay, what we do know that you're treating phonons, so our particles, they have a continuous representation in the space of omega, the normal modes, and we know that the density is related to omega as 3v is the volume divided by 2 pi squared omega squared c tilde to the power 3. Now, this is limited for any omega greater than 0 and smaller than omega Debye. Omega Debye we calculated from the normalization such that the total number of moles, or the total number of particles that we have, is 3n. So we use this in integral between 0 and omega Debye of d omega, the omega equals 3n. Okay. And out of this relation, we obtain that omega Debye is 6n c tilde to the third divided by v cubic root. Great. Now, the next step that we also performed is related to computing the average energy of the system. Okay. Now, the average energy of the system is simply an integral from 0 to omega Debye. So we sum up, we go over all the different particles inside our system, all the different phonons. The omegas represent the different phonons that we have. For each omega, we know how many phonons we have, which is d omega. So this is the amount of phonons that we have per each omega. And here, we're using u of omega, or u omega we call it. Okay. Yes? Pi squared, where we have pi squared. Yeah. So it is 6n. This is c tilde to the third pi squared. Yeah. Thanks. What is u omega? So this is the average energy for a given phonon with a specific omega. And we know that it is minus d to d beta log of z1 of omega, where z1 of omega equals to 1 over 1 minus e to the power minus beta h bar omega. Okay, so I think this is the point where we stopped last Tuesday. So now what we're going to do is to compute u of omega. We're going to substitute the result into this integral, and afterwards we're going to take the derivative of this integral with respect to temperature, and hopefully we will get something useful. Okay, so quite a lot of math today. Keep your seatbelts on. Okay, so what is this? U1 is minus d to d beta of log of 1 over 1 minus e to the power minus beta h bar omega, which is d to d beta log of 1 minus e to the power minus beta h bar omega. We take a derivative of this guy, and it gives us 1 over 1 minus e to the power minus beta h bar omega. We have minus e to the power minus beta h bar omega, and we have minus h bar omega. It's not 1, this is just minus, and in total we obtain, yeah, looks good, h bar omega e to the power minus beta h bar omega divided by 1 minus e to the power minus beta h bar omega. Great. Now that we have, this is u of omega, so the average energy for phonon for specific omega. Okay. Next step is to compute this, the average energy of every body. So whole system, all the different photons, all the particles that we can have inside our system is U over omega, d omega, which is, so we have this guy, so 0 from omega d pi, h bar omega e to the power minus beta h bar omega, divided by 1 minus e minus beta h bar omega. D of omega is this. So we have 3 volume divided by 2 pi squared omega squared c tilde to the third d omega. Okay, now remember, omega d pi is independent of the temperature, which is good, because the next step is to compute Cv, which is du to dt, and we're going to take a derivative with respect to t, and it's very convenient that our upper limit of our integral is independent of the temperature. Otherwise, it could be even more difficult. So now, instead of taking the derivative of t, you see all our expressions are dependent on beta. So it's much more convenient to take a derivative with d to d beta of u and multiply it by the derivative of d beta to dt, which is minus d beta. Beta, remember, it's 1 over k Boltzmann t. So the derivative with respect to t is minus 1 over k Boltzmann t squared. And here we have d to d beta of u. Okay. So what we have is d to the beta of whatever we have on the right hand side of the definition of u, not definition, the form that we obtained for you. So it is minus 1 over k Boltzmann t squared. Now look, there's a lot of different terms inside this integral that are completely independent either of omega or of beta, so we can take them out of the differentiation and the integration. So what is this? Is 3 and v and 2 pi squared and c tilde to the third and h bar. Okay, so we have h bar 3v divided by 2 pi squared, okay, and c tilde to the third. Now I have a derivative of the integral. Now I can switch the the order of integration and differentiation, because nothing really bad happens to this integral, so I assume that the convergence is homogeneous. In other words, we can do this. So we have an integral from 0 to omega d pi. The derivative with respect to beta, so I don't care about the omega over here. I have omega, and I have d to d beta of e to the power minus beta h bar omega divided by 1 minus e to the power minus beta h bar omega d omega. Okay. So
omega squared.
Sorry? Omega squared. Yep. So omega not squared to the third. To the third part.
Yeah.
Okay. Thanks. Alright, so what is this derivative d to d beta of e minus beta h bar omega? 1 minus e minus beta h bar omega. We use the fact that here we have e to the minus beta h bar omega. Here we have e to the minus beta h bar omega. So write this down as d to the beta of 1 minus 1 plus e to the power minus beta h bar omega divided by 1 minus e to the power minus beta h bar omega, which is d to d beta of 1 over 1 minus e to the power minus beta h bar omega. And here we left with minus 1 plus e, so it's basically plus d to d beta of minus 1. Okay. D to d beta of minus 1 is 0. We don't care about this term. So we are left only with the derivative of this 1 over minus 1 over 1 minus e to the power minus beta h bar omega. So what we have 1 minus e to the power minus beta h bar omega squared. We have minus 1. We have e to the power minus beta h bar omega, and we have minus h bar omega. In total, we obtain so we have h bar omega e to the power minus beta h bar omega divided by 1 minus e to the power minus beta h bar omega squared with a minus. Okay, the fact that we got a minus over here, it's very convenient because we also have a minus over here, and in total, since this integral is a summation and derivative of something which is positive, so we expect eventually a positive result. So those two minuses will cancel out, which is good, and at least this is at least a good sign that we haven't made any mistakes so far. Okay, so let's plug in whatever we have left. So U, or I'm sorry, it's CV equals 1 over K Boltzmann T squared H bar 3V 2 pi squared C tilde to the third integral between 0 and omega d pi. And here we have H bar omega to the fourth e to the power minus beta h bar omega divided by 1 minus e to the power minus beta h bar omega to the second power d omega. So we can take out this h bar outside and take e to the power minus beta h bar omega out. So I want to write this as, let's see, so we have h bar squared, or 3 divided by 2 v h bar squared divided by pi squared c tilde to the third K Boltzmann multiplied by 1 over t squared, and an integral between 0 and omega d pi of omega to the fourth, and here I'm going to have e to the beta h bar omega divided by e to the beta h bar omega minus 1 to the second power d omega. I took h bar out and I took e to the minus beta h bar omega out of the parenthesis, so it cancelled out this guy and we got only 1 over here plus. Right. Very nice. Quite very nice. Because, well, first of all, there is no further dancing that we can make, at least for this integral.
It looks like a gamma function is something like that.
Riemann zeta function. We will get over there. It's almost a Riemann zeta function. Okay, so all the mathematicians love Riemann zeta function. There is a very nice theorem about zeros.
Will we prove it?
No. I proved it, but I forgot the proof. No, we haven't. We are not going to prove it. But okay. But now we know only 2 limits. So look, you always in theoretical physics, if you're lucky, really, if you're lucky, you're obtaining a closed form solution in a form of an integral. When you get something like this, you're really, really lucky. Why? Well, although you cannot solve the integral, but numerically you always can. This is A. B, you usually know something about the behavior of the system only in specific limits. It's called a scale separation. We need to obtain either something very small, smaller than everything else in the system, or something really, really, really large, larger than anything else in the system. Only in those limits, usually the physicist knows how to operate and say, well, I know, or I at least can obtain a definite result. So what we cannot do further, or what is our scale separation? Sorry?
of small and big beta.
Or in physics, we can have the limit of small temperatures or the limit of large temperatures. Yes.
What with omega d approach infinity or something like that?
So it's already approaches infinity because it depends on n. Okay, but you need to see, well, infinity with respect to what? So omega d pi, let's write it down again. So omega d pi, so this is the upper limit of the integral. Omega d pi is 6n c tilde to the third multiplied by what? By pi squared divided by v to the third power. Okay, so this can be a large number, a small number. In total, so this is something that depends on n and depends on v. Now, I want to operate in those limits because I believe, or at least the experiment tells me that there are two universal behaviors of almost any solid. Okay? I know that when t goes to infinity, this is a result we know from the Einstein model. It is the specific heat is just k Boltzmann, or specific heat divided by the number of particles that we have inside the system is simply k Boltzmann. Okay? Or 3k Boltzmann. So this is the limit of high temperatures. The limit of low temperatures, we also know that it behaves or decays towards zero as t to the third power. This was the failure, if you remember, of the Einstein model. The Einstein model had extremely fast decay towards zero when t was approaching zero, and the experimental results told us that for many solids, the specific heat decays as t to the third power. So we have two universal behaviors, and this is very good because we then know, or at least hope, that we can take this ugly integral, okay, and obtain its properties, at least in those two limits. Anything else is not really interesting. Not right now. Why it's not really interesting? Because, well, the model is simple. In the first place, we have thrown away huge number of different parameters that might be important. What we believe, and this is the physical intuition where it's coming from, that there are limits when all that we have thrown out of the window, all those parameters, are completely not important. And this is what we think are the limits where the temperatures are extremely low or extremely high. Because something very universal appears in those two limits. Yes?
And so, in the limit of high temperature, why we do not consider phase transition?
Why I would not consider phase transition? Okay, so remember, for what systems we observe phase transitions? We've seen only one system.
It doesn't matter. It holds zero when.
No. The question is in the right place. Okay, and this is an interesting question. Do I expect some sort of phase transition for this system right now? And the answer is probably no. Why no?
It's continuous and
simpler physical answer.
Because when you look at the matter and heat it up, it doesn't change.
The molecule
okay.
Just steady.
One guess per person. One guess per person. One guess per person. Okay. So
It's not guessing if you're.
Shh. Okay. For what phase system we had no phase transition? The ideal gas. Why? There were no interactions, right? So for ideal gas, there were no interactions between the different particles, and this is why we had no phase transition. In the van der Waals gas, there was interactions, right? So we included them effectively in the behavior of the pressure and the volume, and due to those interactions, there was a phase transition. For this system, those particles are what? Independent. Well, that's maybe there is something hidden, but at least when I'm looking at the system, it seems that those are independent particles, phonons, who cares, right? So since they are not really interacting, I do not expect a phase transition. So there can be a gradual, continuous change or whatever, but I do not, at least on first glance, I do not expect any phase transition. Okay, so this is the answer. maybe I'm wrong because the phonons are an effective form of particles, and maybe I'm somehow included in their definition something which might be important, but I don't see it right now. Okay. All right. So we want to operate in those two limits, and in order to operate in those two limits, I want to make the units of the integral unitless. Okay. So the beta h bar omega, I don't like that it's beta h bar omega. I want a single u over here, right? I don't like the d omega.
Choose it to be g or something that's different than u because u is the line of g.
I want that those limits, so why I'm doing this, I want those limits will affect omega d pi, or the upper and the lower limit of my integration. That's the why I'm doing whatever I'm doing, right? So now, so this is a constant, and I don't know what is big, what is small in those two limits, right? But if I somehow affect by t the lower and the upper limit of the integration, maybe I can get out of this somehow. Maybe I can get a large behavior or small behavior. Right now I don't see it. So what we do is we say that beta h bar omega, it is u, right? So du is what? Is beta h bar d omega. So d omega is 1 over beta h bar, which is k Boltzmann t divided by h bar. Okay, so let's substitute it inside. So we have Cv equals to 3 V h bar squared divided by 2 pi squared C tilde to the third k Boltzmann 1 over t to the second power. And inside here we have 0. Okay, so when omega equals omega d pi, we have omega d pi multiplied by h bar and divided by k Boltzmann t. Okay, so this is our upper limit. The lower limit is still 0, so we don't care. Okay. Now what we have inside? We have inside of omega, we have u h bar u multiplied by k Boltzmann t to the fourth power, eu divided by eu minus 1 to the second power, and instead of d omega we have k. What is this?
Is it not divided by h bar?
U over h bar.
U over h bar?
It's divided by h bar.
du. Okay. Yeah.
No,
No.
In the fourth power.
Wait. Here we have, so we'll write down omega equals to k Boltzmann t divided by h bar u. 1 over h bar. Thanks. Okay. Now d omega is what? It is. Wait a second. So d omega, it is 1 over h bar k Boltzmann t du. So it's k Boltzmann t divided by h bar du. Okay. Great. So what we have, let's take everything that is not related to u out of the integral. So we have 3v h bar squared 2 pi squared c tilde to the third k Boltzmann. What we got over here? T to the fourth, t to the fifth. We have t to the fifth. We have k Boltzmann to the fourth, so k Boltzmann to the fifth. We have 1 over h bar to the fifth.
And t squared. In the,
Sorry?
you forgot the 1 over t squared.
1 over t squared. So it was 1 over t squared. And we have an integral from 0 to omega d by h bar by k Boltzmann t, u to the fourth, e to the u, e to the u minus 1, squared du. Now, why I like this representation better than that representation? Because I already told you I'm interested in two limits, t to 0, t to infinity. Now, taking t to 0 doesn't affect anything that is in the integrand of my integral. So the limit of t to 0, t goes to 0, the only thing, well, there is a prefactor and t can be large or small, we will find out really soon, but the integral affected is only in one way. When t goes to 0, 1 over t goes to infinity, so instead of writing this finite integral, I'm writing this as an integral from 0 to infinity, u to the fourth, e to u minus 1, squared du. Okay. And the limit of t goes to infinity, right? I can say, well, this is 0 and the whole integral is 0, but this is not really good, right? To just throw everything out. But when t goes to infinity, I know that this is still an integral from 0 to omega d by h bar by k Boltzmann t. But I know that this value is small, and it's still u to the fourth, e to the u minus 1 to the second power du. But I know that u is small, so I can Taylor expand the function. Okay. So actually, taking those two limits and using this representation of the integral simplifies everything. Okay. Two integrals, two different behaviors. One is from 0 to infinity. The other one is really small, from 0 from some small number. But since this number is small, I don't care about the e to the u minus 1, etc., etc., etc. It's going to be simple. Okay, so first let's look on the t to the 0 limit, because this limit, or you know what, let's look on the t to the infinity limit. So beforehand, let's write down the prefactor. What's the prefactor over here? So we have 3v h bar squared, h bar to the fifth. So we have h bar to the fifth, so 3v 2 pi squared c tilde to the third. It's still the same. Now we have h bar to the second, h bar to the fifth. So 1 over h bar to the third. We have 1 over k Boltzmann to the fifth. So it's k Boltzmann to the fourth. Okay. And we have t to the fifth, t to the third. So it's t to the third. Okay, so this is the prefactor. It's independent of whatever happens to the integral. Okay, so let's first see what happens in the limit when t goes to infinity. Okay, so in this limit, we know that omega d by h bar divided by k Boltzmann t, t is extremely large as you can imagine, and even larger. So this guy goes to 0. Right? So when this guy goes to 0, it's small. U goes to 0. Right? Because we integrate from 0 to a very small number, so u is always small. In this limit, right, so this is u to the fourth, nothing can be done with that. But e to the u minus 1 squared, we can do the following thing. Because u is small, okay, so the nominator simply 1. Okay. We cannot use this approximation in the denominator, because if we submit here 1, it's going to be 1 minus 1 is 0, as 1 divided by 0, it's unimaginably large, and we don't want to see that. So we're going to use this as 1 minus 1 plus u minus 1 squared, okay, approximately, and it equals to 1 over u squared. Okay? So we have an integral between 0 and omega d by h bar divided by k Boltzmann t of what? Of u to the 4th multiplied by 1 divided by u to the 2nd power du, which is an integral from 0 to omega d by h bar by k Boltzmann t of u to the 2nd power du. It equals to 1/3 whatever we have in this upper limit, which is omega d by h bar divided by k Boltzmann t to the 3rd power. Okay, so CV, we're still in this limit of very large temperatures. So CV is, we have this prefactor. 3v2 pi squared c2 to the 3rd 1 over h bar to the 3rd k Boltzmann to the 4th t to the 3rd multiplied by 1/3, and we have this guy, which is 6 and c tilde to the 3rd pi squared divided by v, all of this to 1/3. We have h bar, we have k Boltzmann t to the 3rd power. Okay. Let's see. All right, so let's write it down again. I want to see if I haven't made any mistakes. Okay, 3v 2 pi squared c tilde to the 3rd 1 over h bar to the 3rd k Boltzmann to the 4th t to the 3rd 1/3, and we have 6 and c tilde to the 3rd pi squared divided by v, h bar to the 3rd, k Boltzmann to the 3rd, t to the 3rd. This is the real nice fun part. 3, v. Where's 2? No 2. Pi squared, c to the 3rd, c to the 3rd, h bar to the 3rd, h bar to the 3rd, t to the 3rd, t to the 3rd. What we are left with, k Boltzmann, instead of 4, we have this guy, 6 n divided by 2, which is 3 k Boltzmann multiplied by n. We're happy. Okay, so this is what we expected, right? So this is what Einstein got. This is what we get in an experiment. Very nice. Okay, so this is CV in the t goes to infinity limits. Okay. Yes.
If it were in d dimension, it will be multiplied by d.
So it's in different dimensions. Your density function is different.
Yeah.
Your density function is different, so it's going to be different. It's so basically we will prove today equipartition theorem. I will answer your question. Okay.
Okay.
Okay. The other limit t goes to 2d goes to 0. Okay. T goes to 0. So what we have in t goes to 0, look, the prefactor stays the same. Okay. So we're CV equals to 3v divided by 2 pi squared c tilde to the 3rd k Boltzmann divided by k Boltzmann to the 4th h bar to the 3rd t to the 3rd. So first of all, you already see that we are really good in this limit of small temperatures. Okay? Why? Because, well, the prefactor already have this t to the third. Now, in the limit of low temperatures, instead of this integral, we have this integral. This is basically integral from 0 to infinity of u to the fourth e to the u divided by e to the u minus 1 to the second power du. Okay. And this integral is independent of t. Right? It's a number. We'll calculate this number in a second, but it's a number. So we already see that Cv in the limit when t goes to 0 is proportional to t to the third. So also this limit works really, really, really well. Okay. Now for the curious mathematicians, okay, we will calculate what this number is, although it's not important. So what this number is, so this is an integral from 0 to infinity, u to the 4, e to the u minus 1 squared du. So we can integrate this by parts, right? So integration by parts gives us u to the fourth 1 over e to the u minus 1 minus 1, right? I'm integrating by parts, so this guy, and this is a derivative of something, okay? And this something is this guy, okay? I have a minus over here. And the limits are 0 to infinity minus an integral of 0 to infinity. We have 4 u to the 4 minus 1, and we have minus 1 divided by e to the u minus 1 du. Okay, so this is, for u is 0, it's 0. For u infinity, it's also 0 because of the exponent over here. So in total, no?
that's okay.
Okay. So in total, we're getting that we have 4, an integral from 0 to infinity, u to the 4 minus 1 divided by e to the u minus 1 du. Now you can say, well, Stas, let's try and do the integration by parts again. It won't work. Nothing that you would do work in general, because there is a famous zeta function of x, okay, which is 1 over gamma of x, an integral from 0 to infinity of u to the x minus 1 divided by e to the u minus 1
It's not
du.
definition, it's a form.
It's a form. Okay? So it depends. You can define it as, like this. This is the Riemann zeta function. Riemann zeta function. It's a very famous function in mathematics. There are properties of zeros when this function can get 0 for negative values, and they are very, very important, unproved. So if you want to get an analog of the Nobel Prize for mathematicians, prove something about the zeros of this Riemann zeta function, you'll be very, very famous among mathematicians. It's not a lot of money, but you know, it's a fame.
Still money. Still Nobel.
No, it's not a lot of money.
Still money.
Okay. So this guy eventually, for specific values, it can be obtained. Specifically, in our case, so look what we have. We have so what we have is 4 multiplied by gamma of 4 of zeta of 4, okay. Which is 4 factorial zeta of 4, and I think it equals to pi squared divided by 15, maybe 4 here. Let me check. Yeah. So this. So instead of writing this, we have a number. 4 pi squared divided by 50. It doesn't really matter. Okay, so what is really important, so you have a lot of constants over here.
It should be pi to the. It doesn't matter. It should be pi to the 4.
I think you are wrong.
I
But we'll check this out.
I can put.
You can prove it. Fine. Okay. No, I'll prove it later. So it did it. It's really important. What is really important, it's the t to the third power. If you remember, why we started all this business of Debye, why Debye started this. So the experimental observation of CV as a function of t was like this. This guy was exactly 3K Boltzmann n. Okay. This is an experimental. Einstein had this part, but the function decayed to 0 extremely fast. So this is Einstein. Okay. It was decaying to 0. It wasn't negative never, but it was decaying to 0 extremely fast. So all the difference was this small discrepancy that happens in the limit of small temperatures. What Debye said and have done is basically generalizing Einstein approach, and he indeed obtained this t to the third. So the moment that we are getting this t to the third, okay, we know that Debye was completely right. And what is the big difference between Einstein and Debye? So Einstein said the following thing. Einstein said, I have n particles, each of them have 3 degrees of motion. So in total I have 3 degrees of motion. They don't care about each other. I'm sorry. They don't care about each other. And they vibrate somehow, but, and this is the big thing of Einstein, since the photoelectric effect, is that each mode, each particle, each freedom mode can obtain only quantas of energies. Right? So this is the only thing that we included which wasn't obvious. These quantas of energy that each particle or each mode of freedom can obtain, this is what made the 3K Boltzmann n behavior over here. Now he said, or he has assumed at least, that it will also work for any other temperature, and he failed. Debye used the same approach. He said, well, yeah, of course there's something that's vibrating inside, and at least because of Einstein we know that it's right for the large temperatures, but for small temperatures the particles are somehow correlated. They vibrate together. You remember these waves that I showed to you on the YouTube? So the whole system, it's not that one particle here doing something and the other particle there is doing something. The whole system is doing something together as we go to lower and lower temperatures. So it's not that any modes are possible, or one specific mode. It's just only very specific modes when all the system is doing something together, okay, in coordinated fashion. This limit is important in the limit of flow temperatures, and this is why I obtain a correct result. Okay? So this is the big difference. The quantization of energies are the same in Einstein and in Debye. The only thing is what Debye did, he said, I don't have energy, I don't have particles. I don't know about atoms. They are, well, at the time of Debye we already know that they're atoms. It was already proven. But what is vibrating are not just single particles. They do it together in coordinated fashion. And since they are doing this, I need to approach to this problem differently. I need to define new particles. Phonons, they're not real particles. They're some generalized coordinates of the system. And those coordinates are important. And for those coordinates, only very specific survive in the limit of low temperatures. And they are providing this T to the third. In the limit of large temperatures, I don't really care who vibrates. It can be phonons, it can be real particles. Everybody are completely independent. There are no special modes that are contributing in this regime. Everybody are independent. Everybody are doing something in not a coordinated fashion. This is the limit, completely independent. This is the limit, only very specific modes contribute, and this is why we have a different behavior. Okay. Great, this is nice, but, and that question was asked already previously, well, this limit when CV goes to 3k Boltzmann n, or in general, we have CV divided by 3n goes to k Boltzmann. This limit was obtained by Einstein. This limit in large temperatures. This limit also was obtained by Debye, and we can ask ourselves, maybe it's something universal. Maybe it's something because their particles are completely different. Phonons in Debye's case, regular particles in Einstein's case, but still the same value. So we try to and see this result as an outcome of something very, very general, which I think you encountered already in analytical mechanics, and it's called equipartition theorem. משפט החלוקה שלה. Yeah. So this is part that you learn in your analytical mechanics class. What is equipartition theorem, and why this equipartition theorem? Okay. So the form of equipartition theorem in analytical mechanics is different, but why this equipartition theorem always will get us this universal behavior for high enough temperatures. Okay. All right. So let's look on this equipartition theorem in classical fashion. So you remember, if I have n particles, or let's look on single particle. For single classical particle. So for single classical particle, what do I know? I know that I can write the partition function, right? How I write it? I write it as, instead of a summation, so if I have a particle, I don't have quantized energies, I don't have quantized states. This is something that you have learned in thermodynamics. Is instead of a summation, it's an integration. Okay. From minus infinity to infinity, minus infinity to infinity, of what? 1 over h, so it's h is a Planck constant, not h bar, e to the power u Hamiltonian of q and p, dq and dt. Right, so remember, what is a partition function? So this is classical partition function. Instead of summation, I have integration. Now, instead of a single state, I basically say, well, delta P, delta Q is approximately H, some specific constant, and this is what Gibbs said, well, this is the microstate of the system. This is why we divide it by H. And this is the classical partition function without quantized energies as it was written by Gibbs, and you have seen this result already in thermodynamics. Right. Now, this is a single particle, it does not interact. Now, if I'm assuming the following thing, what is my H, Q, and P? Yes? Minus beta. Yep, so there is a constant. Gibbs had no idea if it's H bar or H, and who Planck did that. And Gibbs wasn't familiar with Planck at all. He just said there is a microstate, and there is a size of this microstate. I will call it H. Now, we call it now H. Why? Because, well, you cannot go lower the uncertainty limit, right? So this is the lowest possible uncertainty that you can have. All right, so what is H and phi? It's important to put it over here beta because it has to be dependent on the temperature somehow. So what is our Hamiltonian? The Hamiltonian, it always comes in the same form. We have p squared, right? P is our momentum, multiplied by some constant, so 1 over 2m. Okay. And we have bq squared. Okay. So this is the simplest Hamiltonian that we can obtain. What is this? This is again a particle that's connected to a spring. So this is the kinetic energy. And this is a quadratic potential energy. So it's potential energy
In some coordinates, right?
okay. Energy in coordinate Q. Now because it's quadratic, we know that we have a harmonic potential. Okay. Great. So this one single particle, it has no interactions with anybody else, and the form of the Hamiltonian is a quadratic form. Why it's quadratic? The momentum enters as a quadratic function, and the coordinate enters as a quadratic function. Okay. Now, we do this double integration. So we have an integral from minus infinity to infinity, minus infinity to infinity of what? We have 1 over h over here, and we have minus beta multiplied by b q squared. We have dq, and we have an integral from minus infinity to infinity e to the power minus 1 over 2m p squared beta of dt. So dp and dq.
No.
Beta B.
Beta B.
Beta and b, large b.
Oh.
Okay, so this the same b that stands over here. You see this? Okay, so those are Gaussian integrals. What is the Gaussian integral? So if I have an integral from minus infinity to infinity of e minus ax squared dx.
The square root of
Pi
pi
of
over
square root of pi.
Okay, so this is a Gaussian integral. So if you must to memorize any integral, what it looks like, what is the value of this integral, memorize Gaussian integral. If you want, I can prove it to you, but it will take like 5 minutes. So we're always using this formula. Now, when we use this formula on this double integration, okay, and it's basically a multiplication of two integrals because the exponential of a sum is a multiplication of two exponentials. That's we can have a separation of the two integrals over here. So what we have from this integral, so z is 1 over h. From the first integral, we have pi divided by beta b multiplied by square root of pi divided by what we have 2 pi m beta. Okay, so make it a big B. The next step is to calculate what is the free energy. So we have one single particle. Who cares about its free energy, but we're still going to calculate it. Why? Because I want eventually to say something about the equipartition theorem, to say something about the specific E, and etc., etc., etc. So the free energy is minus 1 over beta log of z, which is minus 1 over beta log of what we have over here, 1 over h square root of pi beta b pi 2 pi m beta. Yep, we are happy. Okay, so we want to write it down instead of terms of beta in terms of t So F, in terms of T, what we have, minus K Boltzmann T, a log of 1 over H, and here we have a square root of 2m pi squared divided by b, okay, plus 1/2, okay, 1/2 log of K Boltzmann T.
It's 12.
Okay. So this is what we have. Okay. Now, S, the entropy, is minus dF to dt. Okay, so what we have is minus or plus K Boltzmann of log of 1 H square root 2m pi squared divided by b plus K Boltzmann 1 K Boltzmann, okay, and plus K Boltzmann T, right? So multiplied by 1 over T. Have I missed something?
Ln kBt.
1 kBt. KB ln kBt. Looks fine. Looks fine. This part is fine, and I have to take a derivative of this, so I have plus KB ln kBt, and then I have to take a derivative plus kBt. There is something else, right? No? It's fine? 1 over T. Okay. So the last thing that we need to do is to take CV is T ds to dt. Okay. This is the last step. Okay. Now we take a derivative with T. We don't care about this term. We don't take derivative of this term. And the only thing that we get is K Boltzmann T, K Boltzmann divided by T. In total, it is K Boltzmann. So CV, a single particle that has a harmonic potential, okay, that has a harmonic potential and a kinetic energy. The CV is simply K Boltzmann. Okay. Now, we can even separate more, because I can repeat this procedure only for the kinetic energy or only for the harmonic energy. Okay. Now, I started with a particle. It had 2 degrees of freedom, U and P. What I obtained that for each degree of freedom, for single particle, each degree of freedom contributes 1/2 K Boltzmann. So I look on the particle and it has potential energy and it has a kinetic energy. Kinetic energy gives 1/2 K Boltzmann. Potential energy, if I'm assuming or I can approximate my potential energy as a harmonic potential energy, it also contributes 1/2 K Boltzmann. This is why I have CV equals to K Boltzmann. Now, what happens physically at high temperatures? At high temperatures, the probabilities of being in different states are extremely small. The particle can be anywhere, right? Because remember, what is the probability? Probability goes as e to the power minus e to the power minus beta, or let's write it down, 1 over K Boltzmann T of U. When the temperature is very, very large, I have you, and I don't care, I stop caring about interactions. For very large temperatures, the interactions between the different particles become completely negligible. Any particle do whatever it does without looking to the left or to the right, up or down. It doesn't care. What it cares about, its own kinetic energy and its own potential energy. I can always approximate its potential energy as some vibration around the minima, right? So for large temperatures, due to this T over here, and that the probability cancels out all the different interactions, I can say in large temperatures, the particles become non-interacting. And when they are non-interacting, I can look on each and single particle as constituting from particles that have a kinetic energy and particles that have a harmonic energy, harmonic potential energy. This is why it's going to get K Boltzmann. How many particles I have in my system, any system, N, okay, N, and since we're doing all of this in 3 dimensions, each particle doesn't have only P and Q. It can have Px and Qx, Py and P and Qy, and Pz and Qz. So this is why CV got K Boltzmann for each degree of freedom, which includes potential and kinetic energy. And since we in total have 3n different degrees of freedom, we're going always to get this result. So this is why Debye and Einstein and any other model that you will imagine has to satisfy this equipartition theorem. For large temperatures, you always get non-interacting system, and in this non-interacting system, the only way that the specific heat can behave is converge to a specific constant, which is always your K Boltzmann. Okay? You can say, well, this is really nice stuff. Yeah, everything is converging to a constant, but well, in real life, I see other functions. So what usually happens in real life for specific heat is like this. So this is my temperature. This is my CV. So what you are saying is that, well, it starts from 0 and it converges to a constant. Right? So this is what I have said to you. But lo and behold, if you will continue to heat up the system, so this is T, we will continue to heat up the system, you know what will happen? So according to this equipartition theorem, it will always be constant, right? But what actually happens when we heat up the system, we have another step, and then it converges to a constant. So you're not correct. We have step and then another step instead of a convergence to a constant. Where this step coming from, if you have just proven to us that for equipartition theorem for high enough temperatures, you have only K Boltzmann. Where this step is coming from?
You have created new degrees of freedom.
Exactly. I have broken single particles. Okay? So I can imagine that my single particles were molecules. I heated up the system. Each molecule is doing something. They don't care about any other molecules. But what happens over here, so this was my single particle, but my single particle was composed on some other small particles. They were clumped together, combining one single big particle, big molecule. I heated up the system, and the temperature is so high that now even those particles start not to care about each other. You have broken the system, and instead of one particle, I got 1, 2, 3, 4 different particles. So I now have new degrees of freedom. I not invented them, they were clumped together, and now I've broken something by heating up the system. And now again, my specific heat is converging to a constant. I can continue this process once again, and will continue to heat up the system, and eventually I will get something like this. Okay? What happens over here? Each one single particle breaks again to some small particles.
Does it include the phase transition?
Depends. It depends. It can include. It can depend. So what we can actually observe by looking on the specific heat as a function of temperature, and using the simple equipartition theorem, if we obtain those stairs, we know that there is characteristic temperatures, and temperature is K boson T's energy. So there are specific characteristic energetic scales that define transition from one type of system that I have clumped big molecules, to another where I have different particles that are now contributing and moving around. This is related to the phase transition, but we will see later how exactly and why. Now, you don't always see the stairs. Why? Because what happens somehow is maybe this scale is too close to that scale, then all of this is going to be smashed together somehow, and you don't see a separation of different stairs. Right, so this is the case where I don't have a separation of energetic scales in my system. But in some cases I do have, and what have to happen is convergence to a constant, breakage of some internal degrees of freedom, convergence to a constant, and so forth and so on. So this is a very nice result, and we can use this. So think about elementary particles. How we in CERN, not we, how people in CERN actually find new particles. They break them. Okay, so they collide different particles, they use a hammer, and they break something, and then they look inside. So this is a kind of hammer that we have in statistical physics. I want to understand something about the different properties. I can heat up the system, I will break it, and then I will learn about different energetic cooperations that I have inside my system. Yes?
Can I ask again why it did it over and over?
Because I'm assuming that I can always break something.
Okay.
Okay, I'm assuming that I can always break something. It will break because eventually I will get plasma and all different stuff.
Yeah.
And you know about plasma more than me. So I can get some other different properties. But as long as I do not coordinately change something inside the system, right? So this is the picture that I expect to obtain.
If you are taking the system and get the temperature to approach infinity, you will do it in one step.
So I'm starting from 3 degrees Kelvin, and somehow in one step I go to the temperature of the sun somewhere over there. I don't know what will happen.
You don't know if it...
Probably everything will evaporate and I have no idea.
Okay.
All right. Okay. So do you know what is black body radiation?
Yes.
Any other people?
Yes.
Yes. No or yes? So I should explain to you what is black body radiation?
Yes.
Yes. All right. So let's explain what is black body radiation. Yeah.
Black body.
Black body radiation. Yeah, why not? Don't worry, it's going to be quick. Okay, so I have a box, and inside this box I have a radiation. Okay? Now, beforehand I had atoms for Einstein. After that we had phonons for Debye, and now we have photons. Photoni. What is a photon? It's an electromagnetic wave. That's all it is. All right. Now, those photons are wandering inside this cavity, okay, which is also called a Hohlraum in German. And what they do, they penetrate inside the body, and they oscillate the different particles of the body, of the box. And after a while, the box also emit other photons outside. So there are always photons that are getting inside the system, okay, and emitted by the system. Okay, so absorption of photons that are absorbed, and photons that are emitted. Now, in equilibrium, after a while, all the photons that are absorbed are also all the photons that are emitted, and we have an equilibrium, but not of different particles, but actually an equilibrium of photons or equilibrium of the radiation. Okay. Now, usually the setup is that some small part, why small part? Because if it's going to be large part of the radiation that gets out, the equilibrium will cease to exist. So small part is getting out, and by looking on this small part, we can observe the statistics of the photons inside the system. Right? Now, our question is, what is the properties and the statistical properties of the photons inside this cavity? Okay. Now, why it's important? So, if you studied this class, how it's called, modern physics, right? Or ideas in modern physics. So there it was explained that the black body radiation, its historical properties, but there are also two very important practical reasons that we use black body radiation. Okay, so one is CMB, cosmic background radiation. So this is basically the proof why the Big Bang theory is correct. Okay. This is due to, again, statistics of those photons in a closed cavity. And the other one, which is infrared thermometers. Okay. So I probably will explain something about CMB later, but infrared thermometers we all seen during COVID, right? So we have those pistols that people point at you and they say you have now a heat which is extremely high, you should go home. I once tried to enter the university and the guard at the entrance measured my heat and it was 47. So he just jumped backwards and he thought that I have, I don't know, spreading all the COVID in the world. So those infrared thermometers, they are operating because nobody really tells you what is the heat, right? So heat is transferred by particles. So I'm touching something and I'm feeling if it's cold or if it's cold or hot. Why? Because the particles in the pencil are vibrating and somehow affecting my hand and my neurons, and this is how it goes inside my brain. But when we have this infrared thermometers, nobody touches nobody. So this is I'm pointing it somehow and someone, the distance can be large or small, but it's a distance, it's not a zero distance, and I still can tell what's the temperature of this person is. And if actually those thermometers are properly calibrated, they can be extremely precise. So how do they operate? How I can, by measuring from distance and not letting any heat transfer from one place to another, okay, how I can say something about the temperature. Now, this is related to photons because the moment that I say that there is an equilibrium, the temperature of the balls somehow affecting this equilibrium of photons that are absorbed and the photons that are emitted. Okay? And by looking on the photons that are emitted, I can somehow relate the temperature or understand what is the temperature of the body that emitted those photons. So this is the idea of infrared thermometer. I am measuring radiation. This radiation is coming from a body that's assumed to be in equilibrium. The moment the body is in equilibrium, I can understand something or I know something about the temperature of this body. This is the whole idea. The same goes from cosmic background. So I assume that there was something and then there was equilibrium, and I can measure this and understand something about this equilibrium, specifically what happened 300,000 years after the Big Bang. All right, so you probably have seen this. This is why I'm going to explain it a little bit fast of how I relate the temperature to the radiation. Right? This is the whole idea, how to relate the temperature of the body to the radiation that it's emitting and absorbed by some external device. The idea is very simple, and it's actually almost similar to Debye model, although it arrived earlier. Now, there is a very interesting historical story about the black body radiation and the ultraviolet catastrophe, but those people are complaining that I have heard this 4 times, so I won't repeat it. So for our purposes, let's focus on math. Right? We won't talk about the classical ultraviolet catastrophe. What do we understand about the system using the formulas and the equations and the ideas of statistical physics? So what do we have? We have a lot of photons that are getting in and getting out. All those different photons are electromagnetic waves. The photons that are surviving are basically what? Basically radiation and standing waves, right? So we are dealing with standing waves that somehow sit and survive inside this cavity. We already dealt with waves that were surviving in a box. Well, there were acoustic waves. Here are optical electromagnetic waves, but it doesn't really matter. They are still waves. Another assumption that we work really hard for the bimodal, that there are no interaction between the waves. In electromagnetic theory, right, we have a superposition principle. And the moment that we have superposition principle, all the different waves are not interacting. Right? So from the first principles of electromagnetism, we know that all those different photons are non-interacting waves, standing waves, that live inside this cavity. Okay, so remember, we have spent something like 2 hours to prove this for the Debye model. Here we're getting this for free. So I know that we have d omega, which is the density of states, but now what states? The densities of different omegas, because I have again waves over here, that live inside this cavity. What is this? It's again the same v by 2 pi squared. What I have? dk omega, d omega, and I have k of omega. Okay, what is k of omega? For electromagnetic waves. Do you remember? If it's a cavity, I assume it's a vacuum, so it's omega divided by c. C is the speed of light in a vacuum. Okay. Now, for the bimodal, we had longitudinal waves, we had transversal waves. There is something nice about electromagnetic waves. They do not oscillate in the direction of the propagation of the wave, right? They oscillate only in the perpendicular direction to the propagation of the wave. So we only have 2 transversal modes. Okay? So we have d1 over omega, it's v divided by 2 pi squared, 1 over c, this is k squared, right? Omega squared by c squared, and we have d2 or dt1 and dt2. So we have transversal wave. If the wave is propagating over there, I have oscillations in this direction and oscillation in that direction. So I have 2 components, t1 and t2. I don't have t3, I don't have longitudinal, and they're exactly the same because it's a vacuum. dt 2 of omega is v divided by 2 pi squared, 1 over c, omega squared divided by c to the 2nd power. So d of omega, it is v to 2 pi squared over omega squared divided by c to the 3rd. Okay, so instead of 2, in Debye I have here 3. That's the whole difference. And instead of the speed of light, I have some specific speed which we call c tilde. So we erase 2 and 2. And this is the density of states, the density of different photons, right? So I'm basically d of omega. D omega is how many photons I have for a very specific omega. How many photons that are surviving inside this cavity. Okay. Now, so this is part 1. This is about the density. Part 2. Let's treat each photon independently of all the other photons that we have inside the system. And here, where the fun part starts, because we already have done it. So what is z of omega? For a given omega, what is the partition function? Now, there is a classical treatment that leads to crazy result, and this is what's called ultraviolet catastrophe, something completely wrong, okay, based on electromagnetic theory. And there is the Planck idea, right? So what was the Planck idea? That, and this is how the black body radiation was obtained, is that each photon can only have quantas of energies, right? So this is the same idea. Einstein, Debye, Planck, not in the same order, right? It's always, we have particles. The particle cannot have a continuous energy. It can have only quantas of energy. So I fixed omega. I am asking for this given omega, what are the different states? So the energies are n, h, bar, omega. Okay. So I have e to the power minus beta multiplied by 0 plus e to the power minus beta multiplied by h bar omega plus e to the power minus beta 2h bar omega plus. This is again a geometric sum. So z of omega equals to 1 over 1 minus e to the power minus beta h bar omega. Okay. I know this guy, so I can calculate the average energy, right? The average energy per omega. What is the average energy per omega? It is minus d to d beta log of 1 over 1 minus e to the power minus beta h bar omega. Which is d to d beta log of 1 minus e to the power minus beta h bar omega. It equals to 1 over 1 minus e to the power minus beta h bar omega. And here I'm going to have h bar omega e to the power minus beta h bar omega. This is the average energy per particle. Okay. What we have done next in the Debye model, we said, great. U, if we had only very discrete omegas, U is a sum over all the different omegas of U omega. Right? But we don't have a discrete spectrum of omegas. We assume we have some electromagnetic waves, and all the omegas are possible. So this summation goes to an integral over U of omega, d of omega, d omega. The only thing that is left is what are the limits of our integration. So we know, well, there is always the lower limit. Omega goes from 0. What's about the upper limit? So what we had in the Debye model, what was the upper limit of this integral?
The Debye frequency.
The Debye frequency. Why? You remember why we had a Debye frequency? Yes. So because we have a normalization and we had only 3n components, and also because what was oscillating were atoms. So we couldn't have an oscillation where the wavelength is smaller than the distance between the particle. We couldn't. Right? So there was a physical condition that limited the omegas that we had to take into account. This is why we had an upper limit. But for electromagnetic radiation, no. We can have any omega. And you can say, well, stars, but it's going to be an enormous photon, enormously energetic photon. I don't care. It could be. Right? I hope it won't hit me, but it could be there. Right? So I'm going to have an infinity over here. Right? So this is our U. Yes?
But don't we have only photons that are staying in standing waves?
Yep. And I took care of it by introducing d of omega. Right? I'm not saying I have any different omega. How many photons for this given omega I have? D omega. Okay? This is very important. I couldn't just say U omega, D omega. No. There are different amounts of photons for different omegas. And this is described by this d omega. Okay, so what we have left? We have to perform this very long integration. Very long integration. I've already done a lot of integrations today. Okay, so what we need to do, u is an integral from 0 to infinity of h bar omega e to the power minus beta h bar omega divided by 1 over minus e minus beta h bar omega. And inside of d omega we have this guy, which is v omega squared pi squared c to the third d omega. This is nice, but you know, I want to look on the different, not omegas, but the energies of the photons. Right? I want to look on the energies of the photon. Now, the energy of the photon, I can say h bar omega is the energy of the photon, at least the average. Okay, so this is epsilon. So what do I have over here? If I say that h bar omega is epsilon, we know that d omega equals 1 over h bar d epsilon. After performing this substitution, what we're getting, that the average energy, U, is an integral from 0 to infinity. I take this part, which is simply epsilon, which is my energy. Okay. And what I have left is the following. V, instead of omega squared, I have epsilon squared divided by h bar squared, pi squared, right? I have c to the third. I have in place of d omega, I have 1 over h bar. Right? So wait. So I have 1 over h bar to the third. And I have e to the power of minus epsilon, 1 minus e to the power minus epsilon d epsilon. Okay? So this is the energy. This is the average energy that I have. Now look on the form of the integral. The average energy, it is the different energies that I can obtain inside my system multiplied by the probability of seeing this energy. Okay? So this is E, this is F of epsilon, the epsilon, energy,
Beta?
sorry,
Did you forget that?
where I forgot beta,
The exponent.
where, minus beta epsilon, beta epsilon and minus beta epsilon. Thanks. So this is energy, probability, density. Right? By the definition, what is the average energy? Average energy. It equals the different possible energies that I can have inside the system multiplied by the probability density of having this energy, d epsilon. So this F epsilon, this is the spectrum of the energetic or of the energies of the photons that I can obtain. Okay. What we have is V epsilon squared e to the minus beta epsilon divided by pi squared h by to the third c to the third 1 minus e to the power minus beta epsilon. So this density tells me how many energies I'm going to have for this energy, how many photons for this energy, how many photons with that energy. I'm getting a lot of different photons, and this is the probability of getting photons with this specific energy over that specific energy. So this F of epsilon, by epsilon goes like this. Okay. And the exact shape and the exact maximum is t dependent. Okay. Now, if you remember, the classical theory tells us that this spectrum should be like this. Classical theory. Why I don't have a classical behavior but a very different spectrum? Because of those terms. E to the pi minus beta epsilon, y minus e to the minus beta epsilon. Due to the discretization of energies, I obtained that this density is finite, this density does not diverge, right? And this is actually how all the quantum theory started. Okay? Discretization solved the big problem, big puzzle, theoretical puzzle of diverging density of the energy. I will stop here, and in the beginning on the next lecture on Tuesday, I will describe to you, well, you already can guess that I just need to measure the number of photons with different energies, obtain the spectrum, and then I know what's the temperature and how it's related to the cosmic background radiation. So, the beginning of the next lecture, I will spend another 6-7 minutes in order to describe what are the outcomes of this result over here, and what is, because this integral can actually be done. Okay, so we can compute this integral exactly, again using this Riemann zeta function. Thanks.